All right, so we're going to talk about recurrence relations, which are sequences in which the next terms of the sequence are defined by previous terms. At least that's how they're defined. And our goal for this chapter is going to be to find a formula instead of a recursive definition for some sequences. And we're going to be able to do that for certain sequences. So just so we can see what they look like, you might remember we talked about sequences earlier. We have this first one here. So we have to define what I call a seed value or an initial value. So we're told that the first term, which we're calling A0 this time, is 4. And then to get to all the next terms, we add 5 to the previous. So over here is what those terms are going to be. The first term is 4. To get the next one, you're going to add 5. And to get all the subsequent terms, you're going to keep adding 5. So there is an example where we do know what the formula for the nth term is. A sub n is going to be equal to 4 plus 5n. And I didn't mean to put n as a subscript there, but there is the formula there. And as you can see, we have two others there. So I encourage you to try to work through those to get those terms, since we have done recursive sequences before. But one thing I do want to make sure I talk about is the fact that we've been dealing with these for a long time. And that is, factorial is an example of a recursive sequence. If you think about how factorials work, just for example, 4 factorial we know is 4 times 3 times 2 times 1, which is 4 times 3 factorial. So there we know that every factorial has smaller factorials built into it. So if you wanted to write n factorial as a recursive sequence, we would have a sub n is equal to n times a sub n minus 1, where a0 is equal to 1. So there I wrote the seed value last, even though sometimes we usually try to write it first. So either way, as long as you express that seed value, you're fine. Okay, so another example is compound interest. I know you've been exposed to that in earlier courses. You may remember that that's when you deposit money into an account and every year more and more interest gets added. So the interest added is based on what's in the account at the time. So to describe this first term, so at the end of the first year, you know that you're going to have the original amount plus the interest rate times the original amount. And if you factor out P0, you get the 1 plus R. So that means that every year you multiply by 1 plus R to get the next year's amount. And that's what leads to this sequence of values here. And here is the recursive value, or recursive definition for any year. And we know already that for compound interest that this is the expression for the explicit answer, or the explicit solution. So we're not always going to be able to find the explicit formula that easily. That's why we need methods. So we're going to first look at how to form recursive sequences and then see if we could find a definition. And at times we're going to have to use special methodology that we haven't talked about before. So looking at this first one, let's define a recurrence relation for the sequence 0, 4, 8, 12, 16, and 20. This one, fairly simple. We can see that to get to the nth term, we're adding 4 to the previous term, where the first term is 0. And by guessing, you could probably tell that a sub n is equal to 4n. Okay, we're actually going to come up with a way to prove that in the next slide or so. Okay, now and for this next one, and if you want to give it a shot by yourself, pause the video, see if you can come up with it on your own. This one is tricky. But to get the next term, so let's see what's happening here. What are we going to do from 1 to 6? And in the same way, get from 6 to 16, and 16 to 36, and so on and so on. This one's a little tricky. So I'm going to look at the higher terms because if you notice, 76 is roughly twice 36, and 36 is a little bit more than double 16. So I'm thinking that to get to the next term, I'm going to have to take double an minus 1, but notice I don't quite get there. So let's just see what happens here. If I double 1, I get 2, but then I have to do something to get 6. I'm going to say I'm going to add 4. Let's see if that holds the same as we go through the other terms. If I double 6, I get 12. Add 4, get 16. I think we're on to something. Double 16, we get 32. Add 4, get 36. I'm pretty convinced that a sub n is equal to 2 sub a n minus 1 plus 4, and this says that a sub 0 is equal to 1. And there's our recursive sequence. Will we learn how to find the formula for this one? Not necessarily, but just know that there probably is a method to get that. So speaking of getting explicit formulas, when we solve these recurrence relations, it means we're finding an explicit formula. We're no longer relying on previous terms to get terms of the sequence, which means if I wanted to find a sub 10, I no longer need to know a sub 9. I can have a formula to find a sub 10. So there's a couple methods that we can use. Now, we used the naive approach already on that one earlier sequence where we said a sub n was equal to 4n. We guessed a formula. And since it seems to work for the terms that are given, we prove it by induction to show that it works for all n. Something that is a bit familiar to us, I'm sure. Okay, we do have what's called the iterative approach, which I will illustrate later on. I don't tend to use this one as much just because it is more difficult, but it can be done, so we'll see how that plays out. And then we have this method 3, which you can read what that is. It's a special kind of sequence that we're going to focus on in the next section, so stay tuned for that. So, looking at our first example, we're going to solve this one by the naive approach. So we're going to guess a formula, and then we're going to prove it by induction. So let's see how this plays out. So we have a sub 0 equals 0, followed by a sub n is equal to the previous term plus 2n minus 1. So this means we have the terms 0. Now let's see. A sub 1 is going to be a sub 0, this term, 0, plus 2 times 1 minus 1, which is 1. A sub 2 is going to be 1 plus 2. So let's see, a sub 2 is going to be a sub 1 plus 2 minus, not 2 minus 1, 2 times 2 minus 1. So that's 4 minus 1. So this is n equals 2. And that means 1 plus 3, which is 4. A sub 3 is going to be a sub 2 plus 6 minus 1, which is 4 plus 5, which is 9. Are you seeing a pattern yet? Let's just do one more to make sure we guess the right pattern here. A sub 4 is a sub 3 plus 2 times 4 is 8 minus 1. 9 plus 7 is 16. I'm going to say, I think a sub n is n squared. But now what I have to do is prove it. How do I know that somewhere along the line this formula breaks down? So we're going to assume that a sub k minus 1 is equal to k minus 1 squared. Now, why am I going k minus 1? I want to show that the k minus first term plugged into this sequence gives me the kth term, okay? So we're kind of starting one step back. And remember, our base case, we know that a sub 0 is equal to 0 by definition, and we know that a sub 0 by formula is 0 squared, which is 0. So there's our base case. So if we assume that a sub k minus 1 is equal to k minus 1 squared, well then a sub k, which we know is equal to a sub k minus 1 plus 2k minus 1 is k minus 1 squared plus 2k minus 1, which is k squared minus 2k plus 1 plus 2k minus 1. Lots of k's getting thrown around here. And notice, things jump out, and we just end up with k squared. And this proves the formula. Thus, a sub n for this recurrence relation is n squared. And we have solved our first recurrence relation. In the next video, we'll solve another one or two, just to keep going with this whole new thing that we're learning. So, thanks for watching.